Okay, so today we're going to look at power and do a general discussion on the concepts of power, how it relates to work and energy. And then later on we'll take a look at some equations and how to use the power equations to be able to do calculations involving power. So let's go ahead and take a look at concepts. First, who expends more energy during the race, a 100-meter sprinter or the marathon runner? And if you ever watch these races, it becomes quite evident that the marathon runner expends a lot more power, or a lot more energy rather, during the race. But the sprinter actually develops a lot more power. The idea behind that is that power is simply the rate at which work is accomplished, or more generally, the rate at which energy is transferred. So we can write power as work over time, or energy transformed over time. Again, this is the general idea behind power just being the rate at which energy is changed. Oftentimes we think of that energy as being shown as work being done, but it could just be any kind of energy transformation. And then the equations that we would use for that would just be work over time, or since work is force times distance, we can combine the distance and the time here to actually get a velocity. So we can say that power is force times velocity. And we will look at the equations for that later on. You'll see how that equation is used. So whether or not the person runs or walks up the stairs, they do the exact same amount of work. The difference is the power that they develop. So when you run up the stairs, you do the work more quickly. Here we have Michael and Jim. Each do about 200 joules of work. You can see the 200, the 2 meters times 100 newtons would be 200 joules. Michael does that work in 1 second, whereas Jim does that work in 10 seconds. So they both do the same amount of work, but Michael develops more power. And again, this is just a picture of a snowblower. The gas tank is related to the amount of energy storage. So it's how much gas I put into that tank would tell me how much energy, how much work I can actually do. The actual motor here is related to the power. So how quickly can it convert that energy into other forms. And so typically a snowblower might have a horsepower rating of maybe 7 or maybe 10 horsepower, and then the gasoline tank might be able to hold maybe up to half a gallon of gas or so. The units for power, the SI unit is the watt, and the everyday unit that we might use on a more on a basis talking about cars and lawnmowers and so forth would be the horsepower. And the way that those are defined are as such. 1 watt is joule of energy transferred per second, so it'd be 1 watt is 1 joule per second. The horsepower was originally defined based on how much power a horse could develop over any given day. And so this was old school kind of usage for power. And then when we became a little bit more scientific in our measurements, we ended up having to write a conversion factor. So 746 watts is equivalent to 1 horsepower. Just an interesting note about when you're filling your car with gas, just how quickly you are transferring energy to your car when you fill it with gasoline. About 5 gallons per minute. And because of the high energy density of gasoline, we're actually transferring energy to the car at a rate that's equivalent to about 5,000 homes of energy use, electrical energy use. And so just an interesting note about energy versus power. This slide is really just talking about energy density. Here I have a pound of chocolate chip cookies, a pound of TNT, and a pound of gasoline. Which of these has more available energy if I do a per pound basis? And you might be surprised to see that TNT is actually the smallest energy density device or substance out of these three. The gasoline has the most energy per unit pound at 4538 food calories. Chocolate chip cookies is about half of that. And then TNT is actually a very small amount of energy per weight. The catch is that the TNT can convert energy so much more quickly than the others that it can develop a lot more power. And that much greater power means that it can generate a large force, and this is a large force that's ultimately needed to crack concrete in rock and so forth. So TNT is useful because of the rate at which it can convert energy, not because of the amount of energy that it contains. Just a couple of different everyday items to look at the amount of energy that would be contained in them, and then so you can do a comparison. What's really striking about this, I think, is the amount of energy contained in radioactive substances like uranium-235 is the main substance that we would use for a lot of nuclear reactors. And you can see that pound for pound, 1 pound of uranium-235 is equivalent to about 32 million pounds of TNT as far as the equivalent. So it's got a huge amount of energy density. So in a small, compact place, we got a tremendous amount of energy. Over here we have one more slide on conceptual things related to physics and power. An athlete, a sprinter like Usain Bolt here, develops a tremendous amount of power during the race. And behind here is just a graph of their power that like a world-class athlete would develop as they run in a 100-meter race. Usain Bolt only takes around 28 steps or so for the entire race, and you can see that the power that is generated is tremendously high in the beginning, maybe up to 3,000 watts of power, so maybe 4 or 5 horsepower equivalent. But that's done in the early stages of the race, and then as they finish the race, they're developing less and less power. Here they're just moving at a really high speed. Here they're accelerating, and it takes a lot of power to accelerate. You, as just a living being, you generate power just by doing various activities. While you're sleeping, you're burning energy at a rate of about 70 watts. While you're sitting upright, about 115. Light activity, 230 watts. Moderate work, running and bicycling. So you're burning energy at various rates throughout the day. Here we have a picture of a World's Strongest Man competition taking place, where this guy's lifting up a bunch of rocks, and he has to place those on top of these pedestals. Really, this should be called, instead of the World's Strongest Man, it should be called the World's Most Powerful Man. And I made a little joke here about World's Powerfulest Man, but it's the World's Most Powerful Man competition. The person that wins this competition is the person that does the work in the shortest amount of time. So it's really a measure of how much power they're developing. An Ironman race is a race that you burn about 8,000 calories of energy. Is how much energy really needs to be expended during this race. And a typical runner might or athlete might complete this in 12, 13 hours, somewhere in that area. In doing so, if we take the total amount of energy that they expend and divide it by the time that they're expending that energy, you see it's somewhere in the neighborhood of 800 to 900 watts of power that they're developing. So the idea behind the Ironman is that you need to be able to expend energy over long periods of time and do it on a fairly consistent basis. And then last slide here. Here's a person dunking a basketball, and my question to you is, do most people lack the energy to dunk or the power to dunk? And so not many people can actually dunk a basketball. Is it because they don't have the power, or is it because they don't have the energy? And if you think about that, really, if you climbed a stepladder, you would have no trouble going up and dunking a basketball. You would have the energy to be able to lift your body and the ball up to be able to dunk it. Problem is that we don't have a lot of time to be able to do that work. If you consider that most of the work is done during that jumping portion, that's all the time that you have to actually do that amount of work. So you actually lack the power. All the work must be done during a very short interval of time, which is the jump. How much is needed? We'll do a little activity in class where we try to quantify the amount of power developed during a jump. And last but not least, I wanted to share with you just how efficient the human mind is as a not only an energy or information storage device, but also as a energy transformation device. The fastest supercomputers have now topped the human brain in terms of its capacity. You can see the size of this is quite a bit bigger. It looks like it's about 10 times bigger than the human brain as far as the amount of information it can store. This is the fastest supercomputer. And its processing speed is about, maybe about 4 times greater. That's shown by this this portion here. So 8.2 megaflops. You can describe or see what that actually means over here as processing speed. And this would be data storage, so the size of that. But what's really striking is the amount of power that the supercomputer requires to be able to run 9.9 million watts compared to the human brain, only about 20 watts. So even though the fastest supercomputer has more storage and has more processing speed than the human brain, the amount of power that's required to actually operate this thing is so great compared to the human brain that it really tells you how remarkable the human brain is as far as its efficiency. Okay, so that does it for the power concepts. We didn't get into any problems, examples that I've gone through to sort of show you how to solve some problems, so I'm not going to assign any of these things based on today's lesson. Just make sure you've read through the section and you understand what those basic equations are, and I'll show you how to solve some problems on a later lesson.